Welcome to Ultimate Sleep Doctor. Tonight, we'll journey far beyond our own world. Let's consider a distant neighbor, a colossal spiral of stars known as the Andromeda Galaxy. It's a breathtaking sight, a swirling island universe, nearly 1 million light-years away. Our own Milky Way dances with it in a slow, inevitable embrace, a cosmic ballet unfolding across vast, unimaginable timescales. It's a reminder of our place in the grand scheme of things and how wonderfully connected everything is. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift. Let's begin. Long ago, before the twinkling lights of our own Milky Way galaxy dominated the night sky, there was a very different picture. A chaotic, vibrant swirl of gas and dust, a nascent galaxy named Andromeda. It wasn't the stately spiral we observe today, a majestic neighbor some 2.5 million light-years away. Instead, it was a turbulent young galaxy, born from the collision of smaller, dwarf galaxies, a cosmic dance of destruction and creation that shaped its very core. The story of Andromeda's core isn't one of gradual formation. It's a tale of intense, rapid evolution driven primarily by the relentless process of stellar mergers. At the heart of this drama were stars, those brilliant, burning furnaces of hydrogen and helium. They lived, they died, and their deaths, particularly the dramatic ones, were key to building the dense, central region of Andromeda. Initially, Andromeda was filled with stars of all sizes, blue giants, yellow main-sequence stars like our Sun, and red giants, each at different stages of their lives. These stars were scattered across the galaxy's disk, orbiting a central point, but their paths were inevitably going to cross. This wasn't a gentle, organized meeting. It was a violent encounter. When two stars got too close, gravity took over. They began to spiral towards each other, accelerating as they drew nearer. As they collided, the impact wasn't a clean, instantaneous shattering. Instead, it was a complex, multi-stage process. The stars didn't simply explode. They deformed, stretched, and tore apart. These tidal forces, the gravitational pull exerted by the approaching star, created immense streams of gas and dust trailing behind the colliding stars. These streams, rich in heavy elements forged in the hearts of the original stars, were injected into the galaxy's core. Crucially, the stars involved in these mergers weren't always evenly matched in mass. Some were massive, bright blue stars, while others were comparatively smaller, cooler red giants. This disparity in mass played a critical role in what happened next. The massive stars, living short and furious lives, burned through their fuel at an astonishing rate. They ended their lives in spectacular supernova explosions, far more energetic and disruptive than the quieter, slower deaths of less massive stars. These supernovae weren't just flashes of light. They were cosmic shockwaves that compressed the surrounding gas and dust, triggering further star formation. The smaller stars, particularly the red giants, typically died as planetary nebulae, beautiful, expanding shells of gas and dust that slowly dispersed into space. However, even these less dramatic deaths contributed to the core's growth. The material ejected during these nebulae formations provided fuel for newly forming stars, creating a self-sustaining cycle of star birth and death. The process wasn't uniform. Dense clumps of gas and dust, created by the repeated compression from supernovae, began to coalesce under gravity. These dense clumps were the seeds of future massive stars. As they accumulated more and more material, they began to contract, heating up and eventually igniting nuclear fusion in their cores. These newly formed, incredibly massive stars, some significantly larger than our Sun, became the dominant force in the core's evolution. They were incredibly short-lived, burning their fuel with incredible speed and culminating in colossal supernovae explosions. The core of Andromeda wasn't building up gradually, layer by layer. Instead, it experienced periods of intense star formation, punctuated by dramatic, explosive events. These events caused significant disruption to the core's structure, momentarily scattering stars and gas. But the overall trend was upward, a gradual accumulation of mass in the central region. The most massive stars, those born from the compressed material ejected by supernovae, became increasingly prevalent. They were the architects of the core's density. Furthermore, the mergers didn't just create new stars. They redistributed the heavier elements throughout the galaxy's core. Stars are cosmic factories, forging elements heavier than hydrogen and helium in their cores. When these stars died, they flung these elements, oxygen, carbon, iron, back into space, enriching the interstellar medium. This enriched gas and dust then became the raw material for future generations of stars, continuing the cycle of element creation and distribution. The process of stellar mergers and mass segregation wasn't a single event. It was a continuous, ongoing process that spanned billions of years. As Andromeda aged, the rate of mergers slowed down, but the core continued to grow, accumulating mass from the remnants of past collisions. The final shape of Andromeda's core, its high density and complex structure, is a direct consequence of this tumultuous history. Scientists study the motions of stars within Andromeda to piece together this story. By carefully tracking the velocities of these stars, they can infer the gravitational forces at play and reconstruct the sequence of mergers that have shaped the galaxy's core. It's a challenging task, like trying to reconstruct a complex event from fragmented clues, but the evidence is compelling. Andromeda's core is a breathtaking testament to the power of stellar collisions and the beauty of gravitational interactions. The final, incredibly dense region at the very heart of Andromeda, what we now identify as its nucleus, is believed to be the result of the most sustained and intense merger events. Here, the most massive stars had repeatedly collided, creating an extraordinarily compact and hot environment. It is a place of extreme conditions, where the laws of physics are pushed to their limits. And it is, in essence, the solidified legacy of countless stellar dances, a shimmering record etched in space and time. The Andromeda Galaxy, a spiral giant shimmering faintly in the blackness, isn't just a beautiful swirl of stars. It's a complex system, and understanding its structure requires looking beyond the visible, beyond the billions of suns and gas clouds that we can see with telescopes. Much of Andromeda's mass isn't made of anything we can directly detect with light. Instead, it's dominated by something called dark matter, an invisible substance that exerts a gravitational pull, shaping the galaxy's form and influencing the motion of its stars. Scientists believe that dark matter constitutes roughly 85% of Andromeda's total mass. This means that the visible stars, gas, and dust, everything we can see, make up only a tiny fraction of the galaxy's overall weight. The precise distribution of this dark matter is one of the biggest puzzles in modern astrophysics, and astronomers are employing increasingly sophisticated techniques to unravel it. One of the primary ways we're trying to map the dark matter halo is through the study of stellar motions. Stars orbiting the center of a galaxy don't simply move in neat, predictable paths. Instead, they exhibit what's called peculiar velocities, unexpected, random movements that aren't accounted for by the gravity of the visible matter alone. These peculiar velocities are strongest in the outer regions of Andromeda, suggesting the presence of a large, diffuse halo of dark matter, exerting a gravitational influence. Consider a merry-go-round. If you push a child on the edge, they'll spin faster and faster, their path becoming increasingly curved. That's similar to what's happening to stars in Andromeda's outer regions. The gravity of the visible matter, the core and the inner spiral arms, doesn't provide enough gravitational pull to explain their rapid movements. The dark matter halo, extending outwards for millions of light years, provides the extra gravitational force needed to accelerate those outer stars. Gravitational lensing offers another powerful tool for mapping dark matter. This phenomenon occurs when the gravity of a massive object, like a galaxy cluster, or in this case, Andromeda, bends the path of light traveling from a more distant galaxy behind it. The amount of bending reveals the mass of the lensing object. By carefully analyzing the distorted images of background galaxies as seen through Andromeda, astronomers can infer the distribution of dark matter within the galaxy's halo. The observations reveal that Andromeda's dark matter halo isn't a smooth, uniform sphere. Instead, it's characterized by a series of density fluctuations, a sort of clumpy, irregular structure. These fluctuations are similar to the structures seen in the cosmic microwave background radiation, the afterglow of the Big Bang. It suggests that the dark matter within Andromeda formed in a similar way to the large-scale structure of the universe itself. Small density variations in the early universe, amplified by gravity, eventually grew into the vast networks of galaxies and galaxy clusters we observe today. Furthermore, simulations of galaxy formation support the idea of a clumpy dark matter halo for Andromeda. These computer models, based on our understanding of gravity and the initial conditions of the universe, predict that dark matter halos will naturally form in this way, with varying densities and shapes. The observed peculiar velocities of Andromeda's stars are remarkably consistent with the predictions of these simulations, adding further weight to the hypothesis of a clumpy dark matter distribution. The shape of Andromeda's dark matter halo is also a subject of ongoing research. Initial measurements suggested a relatively spherical halo, but more recent studies, particularly those utilizing the Hubble Space Telescope and the James Webb Space Telescope, indicate a more peanut-shaped structure. This elongated shape is most pronounced in the galaxy's southern region and is likely linked to Andromeda's past interactions with the smaller galaxies it has consumed throughout its history. These mergers have distorted the galaxy's shape and, consequently, the distribution of its dark matter halo. The dark matter halo isn't just a passive bystander. It actively plays a role in Andromeda's evolution. The gravitational pull of the halo influences the accretion of gas and smaller galaxies. As Andromeda moves through the universe, its dark matter halo interacts with the surrounding dark matter halos of other galaxies, creating a complex web of gravitational forces. Interestingly, the density of the dark matter halo isn't uniform across all distances. It's generally denser towards the center of the galaxy and gradually decreases as you move outwards. This distribution is consistent with the idea that the halo formed through hierarchical merging, with smaller dark matter halos merging together over time to form the larger structure we observe today. Scientists continue to refine their measurements of Andromeda's dark matter halo, employing a combination of observational techniques, from measuring stellar motions to analyzing gravitational lensing and conducting deep infrared surveys. Each new piece of data helps to build a more complete and accurate picture of this unseen component of our galactic neighbor. It's a reminder that the universe is full of surprises, and that much of its structure remains shrouded in mystery, waiting to be unveiled by the next generation of astronomical observations. The ongoing quest to understand Andromeda's dark matter halo is a testament to the power of scientific curiosity and the enduring human desire to comprehend the fundamental workings of the cosmos. The Andromeda Galaxy, a majestic spiral swirling across the vastness of space, isn't just a beautiful sight. It's a dynamic, ever-changing system, and a significant part of its evolution hinges on a process so spectacular, so violent, that it leaves behind shimmering traces of its power: supernovae. These aren't just ordinary stellar explosions. They are cosmic recycling centers, transforming the very fabric of Andromeda's interstellar medium. The story of Andromeda's chemical makeup is, in large part, a story written in the aftermath of countless supernovae. For millennia, Andromeda's interstellar medium, the gas and dust that fills the space between its stars, was relatively simple. It primarily consisted of hydrogen and helium, the building blocks of the universe. These elements were formed in the Big Bang, and while some heavier elements were created in the hearts of massive stars that lived and died within Andromeda, the vast majority remained confined to the galaxy's core. However, this equilibrium shifted dramatically when stars reached the end of their lives. Massive stars, those giants burning with incredible intensity, possess a limited lifespan. They fuse lighter elements like hydrogen and helium into heavier ones, carbon, oxygen, neon, and so on, within their cores. But eventually they run out of fuel. When a star's core collapses under its own gravity, it triggers a supernova, a catastrophic explosion that rips the star apart. The sheer force of this event is staggering. it briefly outshines entire galaxies. The supernova itself isn't just a blinding flash. It's a meticulously controlled process of nuclear fusion, far more powerful than anything occurring within a star's core. During the explosion, elements heavier than iron, gold, platinum, uranium are created. These elements weren't present in the star's original composition. They're forged in the extreme conditions of the supernova. This synthesized material is then blasted out into space at incredible speeds, carrying with it a wealth of newly created elements. The expanding shockwave from the supernova doesn't just push outwards, it also compresses and heats the surrounding interstellar medium. This compressed gas and dust become incredibly dense, providing the perfect environment for further nuclear reactions to take place. These post-supernova remnants, often appearing as glowing nebulae, are incredibly rich in these heavy elements. Furthermore, the intense heat imparted by the shockwave allows for the formation of even more complex molecules that wouldn't normally form in the relatively cold and dilute interstellar medium. The distribution of these newly created elements throughout Andromeda is remarkably uniform. Scientists have found evidence of this enrichment in nearly every region of the galaxy, though the density of these heavier elements is generally higher in the spiral arms, where star formation is most active. This is because star formation, and therefore supernovae, are concentrated in these areas. The galaxy's spiral arms aren't just beautiful patterns, they're pathways for the dispersal of these newly synthesized elements. The type of supernova plays a role in the specific elements released. Type Ia supernovae, occurring in binary star systems where one star is a white dwarf, are particularly effective at producing iron-rich material. These explosions are remarkably consistent in their energy output, making them excellent standard candles for measuring distances across the universe. But their contribution to Andromeda's enrichment is still substantial. Type II supernovae, arising from the collapse of massive stars, are responsible for the creation of a broader range of heavier elements, from oxygen and neon to more exotic elements like strontium and zirconium. Over billions of years, this cycle of stellar death and rebirth, supernovae followed by the formation of new stars from the enriched interstellar medium, has dramatically altered Andromeda's chemical composition. The galaxy is, in essence, built upon the ashes of its previous generations of stars. The hydrogen and helium that formed the first stars are now heavily contaminated with the products of their explosive deaths. The abundance of elements heavier than iron is particularly noteworthy. It's estimated that Andromeda contains significantly more elements heavier than iron than it did in the early universe. This is because supernovae are the primary source of these heavier elements, constantly replenishing the interstellar medium with their creations. This process isn't just about adding new material. It's about fundamentally changing the properties of the galaxy's building blocks. The interstellar dust grains themselves become coated with these heavier elements, altering their reflectivity and affecting the way light travels through the galaxy. Furthermore, the recycling of material isn't just a one-time event. Stellar mergers, where two galaxies or even two stars collide, further complicate the picture. These mergers bring together stars with different compositions, leading to a further mixing of elements throughout Andromeda. The resulting material is then available for future generations of stars to incorporate, continuing the cycle. Ultimately, the ongoing cycle of supernovae and stellar recycling is what makes Andromeda the galaxy it is today. It's a constantly evolving system, a dynamic tapestry woven from the remnants of countless stellar explosions. The distribution of elements throughout Andromeda is a testament to the power and beauty of these cataclysmic events, and a profound demonstration of the universe's remarkable capacity for transformation and renewal. It's a story written in light, a shimmering record of the galaxy's fiery past and its ongoing journey into the future. The Andromeda Galaxy, a majestic spiral stretching out into the darkness, isn't just a single, solitary island in the universe. It's been a participant in a grand, swirling dance, a series of encounters and mergers that have shaped its appearance, and more importantly, its very composition. These aren't sudden, dramatic collisions like you might see depicted in science fiction. Instead, Andromeda's history is etched in a much subtler way, through the existence of what astronomers call tidal streams. These streams aren't rivers of stars flowing across Andromeda's disk. They're more like faint, distorted filaments of stars, remnants of material that once belonged to smaller galaxies that Andromeda has gravitationally influenced over billions of years. The key to understanding them lies in the fundamental force governing their existence: gravity. When Andromeda's immense gravitational pull exerted upon a smaller satellite galaxy, it didn't simply pull the entire galaxy in. Instead, the galaxy's own gravity stretched and tore at the outer edges of the satellite. This stretching process, driven by the intense gravitational gradients, caused the satellite's stars to be pulled away, not directly into Andromeda, but along elongated, curved paths. These paths are what we observe as tidal streams. Think of it like this. If you were to gently pull on the edges of a stretched rubber band, you wouldn't just rip it apart. Instead, you decreate ripples and distortions that propagate outwards. Similarly, Andromeda's gravity disrupted the orbits of its smaller companions, creating these wispy trails. The streams aren't uniformly distributed. They tend to concentrate in specific regions, particularly in the galaxy's outer disk and halo. These concentrations are where the most significant gravitational disturbances occurred. The beauty of studying these streams is that they provide a direct record of Andromeda's past interactions. Each stream represents a distinct event, a moment when Andromeda's gravity shaped the fate of a smaller galaxy. By meticulously analyzing the stars within these streams, their distances from the galactic center, their velocities, and most crucially, their chemical compositions, astronomers can piece together the sequence of these encounters. The chemical fingerprints of these streams aren't just random. They reflect the makeup of the galaxies they originated from. Specifically, the abundance of certain elements, particularly heavier elements like oxygen, magnesium, and titanium, acts like a unique signature for each stream. These elements are primarily produced in the cores of stars during their final stages of life, through processes like supernovae and stellar winds. Because the streams contain stars that have traveled vast distances, their chemical compositions represent a snapshot of the stellar populations present in the galaxies they came from at the time of the disruption. Comparing these compositions to the overall chemical makeup of the Andromeda Galaxy reveals that these streams are not solely composed of Andromeda's own stars, but rather represent the incorporated material from a diverse collection of smaller galaxies. Current research focuses heavily on identifying and characterizing these streams, and their relative ages are a major area of investigation. The streams aren't all equally ancient. Some are relatively young, likely resulting from more recent interactions, while others are far older, dating back to the early universe, perhaps as far back as 10–12 billion years ago. Determining the age of a stream is complex, but scientists use a combination of techniques. One method involves analyzing the stars' kinematics, their movements through space. Younger streams generally exhibit higher velocities and more chaotic orbits, reflecting the more violent nature of their formation. Furthermore, the spatial distribution of the streams offers clues. Streams closer to the galactic center are typically older, having been subjected to more intense gravitational forces and longer periods of interaction. As streams move further outwards, their characteristics become more diverse, reflecting the increasing variety of smaller galaxies that Andromeda has encountered. The James Webb Space Telescope is proving invaluable in this pursuit. Its unprecedented infrared capabilities allow astronomers to penetrate the dust and gas that obscure the outer regions of Andromeda, providing clearer images of these faint tidal streams. Webb's ability to analyze the light emitted by these stars, the colors and intensities, is allowing for incredibly precise measurements of their distances and velocities, refining our understanding of Andromeda's past. Moreover, the study of tidal streams isn't just about reconstructing Andromeda's history. It provides valuable insights into the broader processes of galaxy evolution in the universe. The interactions between galaxies are a fundamental driver of change, fueling star formation, enriching galactic environments with heavier elements, and ultimately shaping the structure of the cosmos we observe today. Each tidal stream is a tiny piece of evidence, telling a silent story of gravitational dance and cosmic rearrangement. As technology advances and telescopes become more powerful, the intricate details of Andromeda's past and the narratives woven within its tidal streams will continue to be unveiled, offering a deeper understanding of our own galactic home. Andromeda, our nearest galactic neighbor, isn't a solitary giant. Just like our own Milky Way, it's surrounded by a collection of smaller, fainter galaxies, satellites, that have been gravitationally bound to it over billions of years. These aren't just stray lights in the night sky. They're incredibly important pieces of the puzzle in understanding how galaxies form and evolve. For a long time, astronomers suspected Andromeda had a complex family of satellite companions, but proving their existence and understanding their nature required a significant shift in observational technology. The early data, primarily from ground-based telescopes, offered glimpses, but lacked the resolution needed to fully characterize these objects. Then, the James Webb Space Telescope arrived, dramatically changing the game. One of the first and most compelling satellite galaxies to be definitively identified around Andromeda was M32. Initially, M32 appeared as a faint, diffuse smudge within Andromeda's outer halo. It was incredibly difficult to distinguish from the general background starlight. However, with Webb's infrared capabilities, which penetrate dust and gas that block visible light, astronomers were able to resolve M32's shape and reveal its characteristic features. M32 isn't a typical spiral galaxy like Andromeda or the Milky Way. Instead, it's a dwarf elliptical galaxy, a compact, almost spherical shape composed of a tightly packed collection of stars. Its stars are remarkably old, suggesting it has been around for an extraordinarily long time, perhaps since shortly after the Big Bang. Analysis of the light emitted by M32 revealed a significant lack of recent star formation, indicating it has largely exhausted its supply of gas, the fuel needed to create new stars. What's particularly fascinating about M32 is the evidence suggesting it was actively disrupted by Andromeda's gravity. The stellar streams, long, stretched-out trails of stars we previously observed are remnants of M32's former shape. As Andromeda's immense gravitational pull exerted its influence, it began to tear M32 apart, pulling stars from its disk and stretching them into these long, intricate streams. These streams aren't static. They are constantly being modified as Andromeda continues to tug at them. Studying the shapes and velocities of these streams allows scientists to map out the precise forces at play during this tidal interaction. Furthermore, Webb's spectroscopic analysis of the stars in these streams revealed subtle differences in their chemical compositions compared to the stars within the main body of Andromeda. These differences provide clues about the material that was stripped from M32 during the disruption process. Not long after the initial confirmation of M32, astronomers turned their attention to another satellite galaxy, M110. M110 presented a different but equally captivating challenge. It appeared as a much fainter and more diffuse object than M32, requiring even greater sensitivity from Webb. M110 is considered a dwarf irregular galaxy, meaning it lacks a regular, defined shape like spirals or ellipticals. It's a tangled mess of stars and gas, appearing almost chaotic in its distribution. What's truly remarkable about M110 is the discovery of a surprisingly bright, diffuse bridge of stars connecting it to Andromeda. This bridge, again, is a direct consequence of tidal interactions. It's formed by the gravitational forces of Andromeda pulling on M110, creating a pathway of stars that now connects the two galaxies. The bridge isn't a solid, continuous structure. It's a complex, fragmented network of stars, reflecting the ongoing disruption. Webb's infrared data has been instrumental in revealing this bridge's intricate details, showing how the gravitational pull is reshaping the galaxy. The spectroscopic analysis of stars within the bridge and M110 offered an unprecedented look at the conditions in the disrupted material. Scientists have found that the bridge's stars have a very different chemical composition from those found in Andromeda's main body, suggesting that M110 had a much more diverse and younger stellar population before it was significantly affected. The study of M32 and M110 and the bridges connecting them to Andromeda isn't just about cataloging distant objects. It's a window into the processes of galaxy formation and evolution. These tidal interactions are remarkably common, and they represent a crucial phase in the lives of smaller galaxies. These satellite galaxies are acting as cosmic laboratories, allowing astronomers to study how gravity shapes galaxies, how material is recycled between them, and how stars form and die within these disrupted environments. As Webb continues to observe Andromeda and its satellites, scientists expect to uncover even more details about these interactions and refine our understanding of the complex relationships between galaxies in the universe. The data from M32 and M110, collected with the immense power of the James Webb Space Telescope, is already providing invaluable insights, painting a richer and more detailed picture of our galactic neighborhood and the grand dance of the universe. Andromeda, our galactic neighbor, isn't just a serene spiral, a beautiful island in the cosmic ocean. Beneath its majestic appearance, a far more energetic and dramatic story is unfolding, a story centered around what scientists call active galactic nuclei, or AGN. These aren't normal stars. They're the engines of extraordinary power, and within Andromeda, they represent some of the most intense phenomena we observe in the universe. The key to understanding these AGN lies in the heart of their galaxies, supermassive black holes. These black holes, millions or even billions of times the mass of our Sun, sit at the center of Andromeda, silently pulling in matter and, crucially, releasing tremendous amounts of energy. The processes occurring within these central regions are driven by accretion. Material, gas, dust, and even stars spirals inward towards the black hole, forming a swirling disk known as an accretion disk. As this material gets closer, it's subjected to immense gravitational forces, and friction between the particles within the disk causes it to heat up to unbelievably high temperatures, hotter than the core of our Sun by many orders of magnitude. This extreme heat generates intense electromagnetic radiation across the spectrum, from radio waves to X-rays. This radiation is the initial, observable signature of an AGN. But the story doesn't end with the accretion disk. Much of the energy released isn't confined to the disk itself. A significant portion of the material, particularly the most energetic particles, gets launched outwards, creating spectacular structures known as jets. These jets are beams of plasma, superheated gas, and magnetic fields that shoot out from the poles of the black hole, often extending for millions of light years into intergalactic space. The exact mechanism that launches these jets is still a subject of intense research, but it's believed to be linked to the black hole's powerful magnetic field. The magnetic field, generated by the rotating plasma within the accretion disk, acts like a colossal funnel, channeling and accelerating the particles. As the particles gain speed, they become relativistic, meaning they travel at speeds approaching the speed of light. This acceleration process is what allows the jets to achieve such incredible velocities and luminosities. It's a testament to the raw power contained within these objects. Within Andromeda, the AGN, centered around the supermassive black hole known as M31, pronounced M31 star, exhibits particularly strong jet activity. Observations made with telescopes like the Very Large Telescope, VLT, and the Hubble Space Telescope have revealed remarkably powerful jets emanating from this central region. The jets aren't just bright, they're incredibly polarized, meaning the light they emit is preferentially aligned in certain directions, a direct consequence of the strong magnetic fields involved in their formation. The energy output of M31's AGN is astonishing. It's one of the most luminous AGN we know of, shining with the equivalent of billions of suns. This immense energy isn't just a passive glow. It actively impacts the surrounding intergalactic medium. The jets, interacting with the gas and magnetic fields of the region around Andromeda's core, create enormous cavities and disturbances. These cavities, sculpted by the relentless barrage of energy, can be seen as distinct regions of lower density within the galaxy's halo. Moreover, these jets play a role in the chemical enrichment of Andromeda. As the particles within the jets collide with the surrounding gas, they deposit energy and heavy elements heavier than hydrogen and helium, into the galactic halo. This process contributes to the overall metallicity of Andromeda, a key factor influencing the formation of stars within the galaxy. The jets, in essence, are cosmic delivery systems, spreading the building blocks of new stars throughout the galaxy's vast expanse. The study of Andromeda's AGN provides crucial insights into the evolution of galaxies. It demonstrates that supermassive black holes aren't just passive bystanders. They actively shape the environments around them, influencing the growth and development of their host galaxies. The feedback mechanism, the process by which the AGN's energy output affects the galaxy, is now recognized as a fundamental component in the overall evolution of galaxies, including our own Milky Way. Scientists are continuing to refine their models of jet formation and propagation. They're using advanced simulations and observations to better understand the complex interplay between gravity, magnetic fields, and plasma. The investigation of M31's AGN, along with similar AGN found in other galaxies, is revealing a dynamic and intricate picture of how the universe functions, a picture still being painted with every new observation. The ongoing research promises to unlock even more secrets about these powerful engines of the cosmos, forever changing our understanding of galactic evolution. Andromeda, our nearest galactic neighbor, isn't just a large, glowing disk in the night sky. It's a surprisingly complex structure and a truly fascinating puzzle for astronomers. Much of that fascination stems from its spiral arms, those magnificent, swirling bands of stars and gas that seem to reach out into the darkness. Understanding how these arms formed and why they remained stable for so long is a key part of unraveling the story of Andromeda's evolution. The initial picture astronomers had of spiral galaxies, including Andromeda, was quite simple. They envisioned a steady flow of gas, pulled inwards by gravity, continuously replenishing the spiral arms and maintaining their beautiful shapes. This was the density wave theory, a tidy explanation suggesting a slow-moving wave of disturbance propagated through the galaxy, triggering star formation in its wake. However, observations of Andromeda challenged this straightforward model. The arms appeared too rigidly structured, too clearly defined, and crucially, didn't seem to be constantly overflowing with new material. Detailed mapping of the stellar populations within the arms revealed a surprising characteristic. The stars weren't uniformly distributed in a way that expected constant replenishment. Instead, the stars within the arms showed distinct age groupings, a remarkable strangeness for a galaxy continuously building up its spiral structure. Younger, hotter, bluer stars were concentrated in the inner regions of the arms, while older, redder stars dominated the outer regions. This age sequence wasn't a natural consequence of continuous accretion. It suggested a more complex process had been at work. The current prevailing theory, largely supported by simulations and observations, points toward a model based on self-organized spiral structure. This doesn't involve a single external wave. Instead, it posits that the spiral arms emerge from instabilities within the galactic disk itself. Think of it like a ripple in a pond. A disturbance initially sets up a wave, but that wave doesn't simply propagate outwards. Instead, it interacts with itself, creating a repeating pattern. Within Andromeda's rotating disk, regions of slightly higher density, perhaps caused by subtle variations in the gravitational field or localized disturbances, can act as seeds for spiral arm formation. As the disk rotates, these density fluctuations are amplified, leading to the formation of spiral arms. The key is that this process doesn't rely on an external driver. The galaxy's own rotation and the gravitational interactions within its disk are sufficient to create and sustain the spiral structure. These nascent spiral arms then undergo a process called arm buckling. As the arms rotate, the gravitational forces acting on the gas and stars within them are not perfectly aligned. The stars, moving at different speeds, experience varying gravitational pulls, causing the arms to distort and buckle. These buckles, in turn, generate new disturbances, further reinforcing the spiral pattern. It's a self-regulating feedback loop, a delicate balance between compression and expansion that allows the spiral arms to maintain their shape for billions of years. The observed strangeness, the age sequence in the arms now fits neatly into this picture. The inner arms, where the compression is greatest, experience the strongest gravitational forces, leading to the formation of younger, hotter stars. As you move outwards, the compression weakens, allowing older stars to survive and dominate. This isn't a random scattering of stars. It's a direct consequence of the differential gravitational forces shaping the spiral arms. Furthermore, the stability of Andromeda's spiral arms is profoundly affected by the galaxy's dark matter halo. This invisible, enigmatic substance extends far beyond the visible disk, providing a vast gravitational scaffolding that helps to maintain the overall shape of the galaxy and, crucially, stabilizes the spiral arms. The dark matter halo provides the extra gravitational force needed to counteract the centrifugal forces generated by the galaxy's rotation, allowing the arms to remain intact despite the ongoing turbulence. Simulations incorporating dark matter halos have been remarkably successful in reproducing the observed morphology of Andromeda's spiral arms. These simulations demonstrate that the interplay between the dark matter halo, the galactic disk, and the rotation of the galaxy is sufficient to create and maintain the spiral structure. The arms aren't simply passively shaped. They are actively created and sculpted by this complex gravitational dance. It's important to note that this model isn't without its challenges. Precise measurements of the galaxy's rotation curve, how the speed of stars changes with their distance from the galactic center, still present some subtle discrepancies that scientists are actively investigating. However, the self-organized spiral theory, combined with the influence of the dark matter halo, provides the most compelling and widely accepted explanation for the structure and stability of Andromeda's magnificent spiral arms. As we continue to study this neighboring galaxy, we'll undoubtedly gain further insights into the fundamental processes that shape galaxies throughout the universe. Andromeda, our nearest galactic neighbor, isn't just a swirling, magnificent spiral. It's a cosmic tapestry woven with incredibly diverse communities of stars. For decades, astronomers have been diligently studying these stellar groupings, and what they've discovered is revealing a remarkable history of formation and evolution within the galaxy itself. A key element in this investigation has been the careful analysis of star clusters and understanding the distinctions between two primary types, population II and population I clusters. These categories aren't simply labels. They represent dramatically different origins and characteristics for the stars contained within them. The story begins with population II clusters. These are the oldest stellar groupings we find in Andromeda. They're like ancient, quiet harbors, containing stars that have been around for an extraordinarily long time, typically over 10 billion years. These stars are predominantly composed of iron, a metal, far more so than the stars we see in our own Milky Way. This high iron content is a hallmark of stars formed in the very early universe, when heavier elements hadn't yet been widely dispersed throughout space. The formation of these clusters occurred in the dense, primordial gas clouds that existed shortly after the Big Bang. Because of their age, the stars within population II clusters have often undergone significant changes. Many have shed their outer layers through a process called stellar winds, creating beautiful, expanding shells of gas surrounding the core of the cluster. Furthermore, these clusters tend to be found in the more diffuse regions of Andromeda, often at greater distances from the galactic center, where the density of gas is lower. Their low metallicities and scattered appearance provide a snapshot of the early conditions of the galaxy's formation. Then there are the population I clusters, a markedly younger and more vibrant cohort. These clusters are significantly more metal-rich, meaning they contain a lower proportion of iron and other heavier elements compared to population II clusters. This difference in metal content is crucial because it reflects their origin. They formed from gas clouds that had already been exposed to the products of previous generations of stars. The stars in population I clusters are generally much bluer and hotter than their older counterparts, and they're typically found closer to the galactic center, where the density of gas and dust is highest. They represent the new arrivals in Andromeda's stellar community, forged from material that had undergone multiple cycles of star formation and death. The processes involved in creating these clusters are deeply intertwined. Population II clusters likely formed from the collapse of giant molecular clouds in the early universe, largely untouched by subsequent star formation. As these clouds fragmented and coalesced, the initial stars that formed within them were relatively pristine, containing only the elemental abundances present at the time of their birth. These stars, over billions of years, would gradually enrich the surrounding interstellar medium with heavier elements through supernovae explosions, massive stellar deaths that scatter elements across space. This enriched material then became available for the formation of new, younger star clusters, the population I clusters. The study of these clusters isn't just about understanding the individual stars within them. It's about piecing together the entire history of Andromeda's evolution. By analyzing the ages, compositions, and spatial distributions of the clusters, astronomers can model how the galaxy accumulated material, how star formation rates changed over time, and how the galaxy's overall structure evolved. For example, the density of population I clusters near the galactic center suggests a period of intense star formation driven by the availability of gas and dust. Conversely, the relatively sparse distribution of these clusters at larger distances indicates a decline in star formation as Andromeda matured. Furthermore, the study of stellar streams, elongated groups of stars that are being pulled apart as they orbit Andromeda, provides another valuable source of information. These streams are remnants of smaller galaxies that have been cannibalized by Andromeda. Analyzing the stellar populations within these streams, particularly the populations of population I stars, helps astronomers to map the gravitational field of Andromeda and to understand the dynamics of this galactic merger. The differences between population II and population I clusters aren't just about age and metal content. They're fundamentally linked to the very processes that govern the birth and death of stars. Studying these clusters allows us to observe and interpret the remarkable sequence of events that have shaped Andromeda from its very beginnings to its current, majestic state. It's a story written in the light of countless stars, a testament to the enduring power of gravity and the cyclical nature of the universe. Ultimately, by meticulously examining these stellar groupings, we gain a deeper appreciation for the complex and dynamic history of our galactic neighbor, Andromeda. The Andromeda Galaxy, a majestic spiral stretching across our cosmic neighborhood, isn't just a beautiful swirl of stars. Within its vast expanse, A quieter, more intricate dance is underway, the movement of its globular clusters. These dense collections of ancient stars, relics from the early universe, aren't passively drifting. They're responding to the gravitational tugs and subtle forces shaping Andromeda's overall structure. Studying their motions offers a remarkable window into the galaxy's hidden dynamics. Globular clusters, like tiny, self-contained universes, typically contain hundreds of thousands or even millions of stars. They're remarkably old, having formed billions of years ago, and many are remarkably metal-poor, meaning they lack the heavier elements forged in the hearts of stars. Because of this, they provide a pristine snapshot of the conditions present shortly after the Big Bang. Their precise movements are governed by the same fundamental laws of gravity that dictate the motion of planets around a star, but on a vastly larger scale. Astronomers primarily use the Hubble Space Telescope and increasingly the James Webb Space Telescope to observe these clusters and measure their velocities. This isn't a simple, straightforward process. The light emitted by the stars within a globular cluster, particularly the fainter ones, is incredibly weak. Therefore, simply looking at their brightness over time isn't enough to determine their speed. Instead, scientists utilize a technique called proper motion measurement. This involves carefully tracking the tiny, seemingly imperceptible shifts in a cluster's position against the backdrop of more distant stars. It's like watching a tiny boat bobbing on a vast ocean. The boat's movement itself doesn't tell you how fast it's going, but its movement relative to the surrounding water does. The process starts with identifying a globular cluster center of mass. This is the point where the gravitational pull of all its stars is concentrated. Then, astronomers meticulously track the positions of several bright stars within the cluster over months or even years. By measuring these changes in position, they can determine both the cluster's radial velocity, its speed along our line of sight, and its proper motion, its movement across the sky. Radial velocity, in particular, is crucial because it tells us how fast the cluster is moving towards or away from us. But simply knowing a cluster's speed isn't enough to fully understand its dynamics. The gravitational potential of Andromeda plays a dominant role. The galaxy's mass, concentrated primarily in its central bulge and spiral arms, exerts a powerful pull on all its components, including these globular clusters. The shape of this gravitational potential, whether it's smooth or uneven, significantly affects the trajectories of the clusters. A smoother potential means clusters tend to follow relatively straightforward orbits, while a more complex, irregular potential introduces twists and turns. Computer simulations play a critical role in this investigation. These models attempt to replicate the observed motions of the globular clusters, taking into account the overall mass distribution of Andromeda, the galaxy's dark matter content, a mysterious, invisible substance that makes up a significant portion of Andromeda's mass, and the gravitational interactions between the clusters themselves. These simulations aren't perfect, of course. Dark matter, by its very nature, is incredibly difficult to detect directly, and modeling the complex gravitational interactions between numerous clusters is a computationally intensive task. Interestingly, the globular clusters aren't all moving in perfect circles. Their orbits are often elongated and distorted, reflecting the non-spherical nature of Andromeda's gravitational potential. Some clusters appear to be orbiting in what are described as perturbed orbits, where their paths deviate noticeably from simple elliptical trajectories. This suggests that they're experiencing gravitational resonances with other features within the galaxy, like spiral arms or denser concentrations of stars. Furthermore, the observations show that the speeds of globular clusters generally decrease as they move farther away from the galactic center. This isn't entirely unexpected. The gravitational pull of the galaxy weakens with distance. However, the extent of this decline and the specific patterns of velocity dispersion, the range of speeds within a cluster, offer valuable information about the distribution of mass within Andromeda, particularly the distribution of dark matter. A higher dispersion indicates a more uneven distribution of mass. The study of globular cluster orbits also reveals a surprising aspect of Andromeda's evolution. Many of the clusters appear to have been stirred up or disrupted during periods of intense star formation, when the galaxy was undergoing periods of rapid growth. These disruptions likely resulted from gravitational interactions with younger, denser populations of stars within the galaxy. Currently, scientists are using spectroscopic data, analyzing the light from the clusters to determine their composition and velocity, to refine these models and understand how the interactions between globular clusters and the galaxy's broader structure have shaped Andromeda's history. The data continues to shed light on the complex interplay between these ancient stellar remnants and the dynamic evolution of the galaxy itself. As observation technology advances, our understanding of these orbits will only become more precise, painting an even more detailed picture of Andromeda's past and future. Determining how far away Andromeda truly was presented a profound challenge to astronomers in the 20th century. Early estimates, based on apparent brightness and assuming a uniform distribution of stars throughout the galaxy, were wildly inaccurate, suggesting a distance far closer than what the galaxy's observed size actually indicated. These initial measurements were like guessing the size of a vast ocean simply by looking at a single wave. The apparent size didn't reflect the true extent of the water. The problem wasn't a lack of interest, but rather the fundamental difficulty in discerning the true intrinsic brightness of incredibly distant objects. It was like trying to gauge the size of a city solely from its reflection in a distant puddle. The reflection itself is distorted and incomplete. The key to unlocking Andromeda's distance lay in a revolutionary concept, brilliantly articulated by Henrietta Leavitt in the early 20th century. Leavitt, working with observations of Cepheid variable stars, discovered a remarkable relationship, a period luminosity relationship. Cepheid variable stars are a special type of star that pulsates, increasing and decreasing in brightness in a predictable pattern. Crucially, the longer the period of pulsation, the time it takes for a star to go through one complete cycle of brightening and dimming, the more luminous, or bright, the star actually is. This wasn't a random correlation. It was a consistent, predictable connection. Think of it like a flickering light bulb. If a bulb flickers slowly, the amount of light it emits during its brightest phase is considerably higher than if it flickered rapidly. The speed of the flicker, or the pulsation period, directly dictates the star's inherent brightness. Leavitt meticulously plotted the period of pulsation against the apparent brightness of a collection of Cepheid variable stars, and what she found was startlingly clear: a linear relationship. She observed that as the period increased, so did the luminosity, and the slope of this line was remarkably consistent across different stars. This discovery was profound because it meant that astronomers could use these pulsating stars as standard candles. A standard candle is an object with a known intrinsic luminosity, its true brightness, allowing astronomers to calculate its distance. The principle is straightforward, but extraordinarily powerful. If you measure the apparent brightness of a Cepheid variable, how bright it appears to us on Earth, and you know its true brightness, you can calculate the distance using the inverse square law. The inverse square law is a fundamental principle of physics. It states that the intensity of light decreases with the square of the distance from the source. Imagine shining a flashlight. The light spreads out in all directions, and the brightness decreases rapidly as the distance increases. If you double the distance, the brightness becomes 1/4 of the original. If you triple the distance, the brightness is 1/9, and so on. Astronomers could apply this law to measure the apparent brightness of a Cepheid, and combining that with the period luminosity relationship, determine the distance. The first major use of this technique came with Andromeda. Astronomers like Edwin Hubble and his team began systematically observing Cepheid variables within the galaxy. They identified a number of these pulsating stars, carefully measuring their pulsation periods and, consequently, their intrinsic luminosities. They then compared these measured luminosities to their apparent brightnesses as seen from Earth. The results were truly astonishing. The distance derived from the Cepheid variables was significantly larger than the distance estimated using other, less reliable methods. It indicated that Andromeda was far further away than previously thought, approximately 2.5 million light-years. This distance was, and still is, the gold standard for measuring the distances to galaxies beyond our own. The Cepheid variables essentially provided a crucial yardstick for the universe. However, it wasn't without its challenges. The inherent brightness of a Cepheid variable can be affected by factors such as its composition and age. Astronomers had to carefully account for these potential influences when determining its intrinsic luminosity. They developed sophisticated techniques to correct for these effects, ensuring the most accurate distance measurements possible. Furthermore, finding Cepheid variables within Andromeda was a painstaking process. These stars are relatively rare, and they are often obscured by dust and gas within the galaxy, making them difficult to detect. Despite these difficulties, the continued use of Cepheid variables, alongside other distance measurement techniques like Type Ia supernovae, has become fundamental to our understanding of the scale and evolution of the universe. The legacy of Henrietta Leavitt's discovery continues to illuminate the vast distances between galaxies, helping us piece together the history of the cosmos. The vastness of Andromeda, our nearest galactic neighbor, isn't just about its sheer size, over 100,000 light-years across. It's a complex arena sculpted by gravity, and within this arena, a particularly curious phenomenon reveals itself: gravitational lensing. This isn't a sudden, dramatic distortion like you might see with a strong lens focusing sunlight. Instead, it's a subtle, almost ghostly bending of light, orchestrated by the immense gravity of Andromeda itself, and to a lesser extent, by the numerous stars within it. The closer a galaxy is to Andromeda, the more pronounced this lensing effect becomes. The basic principle behind gravitational lensing is rooted in Einstein's theory of general relativity. Mass warps the very fabric of space and time. When light, which always travels in a straight line, passes near a massive object, its path is deflected. Think of it like a marble rolling across a slightly curved trampoline. It won't travel in a perfectly straight line. It'll curve around the depression created by a heavier object. Light behaves in a similar way, albeit far more delicately. Andromeda's gravity is so powerful that it can bend the light from galaxies located far behind it. These background galaxies, incredibly distant and often incredibly faint, appear distorted. They don't just appear brighter, they often appear as arcs, rings, or multiple images of the same background galaxy. The degree of distortion depends on the mass of the lensing object Andromeda, and the distance to both the lens Andromeda and the background galaxy. The closer the background galaxy is to the line of sight, the greater the effect. Scientists use these distorted images as a valuable tool for studying galaxies that would otherwise be impossible to observe directly. The background galaxies are so faint that their own light is overwhelmed by the light that has been bent around Andromeda. Without lensing, we'd miss them entirely. However, the distorted light reveals properties of these background galaxies that we couldn't otherwise measure. We can determine their redshifts, which is a measure of how much their light has been stretched due to the expansion of the universe. This, in turn, allows us to calculate their distance and velocity. It's not just the main galaxy that contributes to this lensing. Andromeda contains billions of stars, and even a single, massive star can create a measurable lensing effect, although much weaker than that caused by the entire galaxy. The distribution of mass, stars, dark matter, and gas within Andromeda is what ultimately governs the strength of the lensing. More massive objects produce stronger distortions. Furthermore, the effect isn't uniform. Because Andromeda isn't a perfectly smooth sphere, the lensing patterns are complex, varying across the sky. This means astronomers have to meticulously map the distribution of mass within Andromeda to accurately interpret the lensing observations. They use sophisticated computer models and statistical analysis to disentangle the different lensing components. One fascinating aspect of this phenomenon is the discovery of Einstein rings. These are complete, circular rings of light formed when a background galaxy lies precisely on the line of sight to Andromeda. It's as if Andromeda is acting like a perfect cosmic magnifying glass, creating a complete halo of light around itself. Finding and characterizing these Einstein rings offers a unique, three-dimensional view of the mass distribution within Andromeda. The study of gravitational lensing around Andromeda has also provided crucial evidence for the existence of dark matter. Dark matter doesn't emit, absorb, or reflect light, so we can't see it directly. However, its gravitational effects, like the distortion of light, are observable. By analyzing the patterns of lensing, scientists can infer the presence of unseen mass, primarily dark matter, that surrounds and permeates Andromeda. The distribution of dark matter greatly influences the lensing effects. Beyond simply observing the distortions, astronomers are developing techniques to fingerprint the galaxies that are being lensed. By carefully analyzing the shapes and positions of the distorted images, they can determine the intrinsic shapes and sizes of the background galaxies, information that would otherwise be impossible to obtain. It's like reconstructing a shattered vase from its fragments, using the distortions as clues. The Hubble Space Telescope and the James Webb Space Telescope have revolutionized the field of gravitational lensing studies. Their increased resolution and sensitivity have allowed astronomers to detect fainter, more distant lensed galaxies and to probe the lensing effects with unprecedented precision. These powerful telescopes are allowing us to study the very early universe, galaxies, that formed shortly after the Big Bang, through the distorted light of galaxies being magnified by the gravity of Andromeda. The ongoing research into gravitational lensing around Andromeda is not just about understanding our galactic neighbor. It's about unlocking the secrets of the universe itself. It's a testament to the power of indirect observation and the remarkable ability of Einstein's theory to predict and reveal the workings of the cosmos. The subtle distortions of light, orchestrated by the immense gravity of Andromeda, are offering us a window into the distant past, the distribution of dark matter, and the fundamental nature of space and time. The universe, even when appearing serene, holds secrets that shimmer just beyond the reach of our most sophisticated instruments. For decades, astronomers have been grappling with a fundamental question about our own existence. Why is there more matter than antimatter in the observable universe? The Big Bang theory suggests equal amounts of both should have been created, but when matter and antimatter annihilate upon contact, only matter remains. This imbalance is a profound mystery, and one that has led scientists to look for clues, particularly in galaxies far removed from our own Milky Way, like Andromeda. The hunt for antimatter in Andromeda isn't about finding tiny, fleeting particles in the traditional sense. It's a quest to detect subtle anomalies in the galaxy's radiation that might betray the presence of exotic particles that could have formed in conditions vastly different from those present during the Big Bang. Andromeda, being the closest large galaxy to us, offers a unique opportunity. Its immense size and relative brightness allow for detailed observations that are impossible to achieve with other galaxies. The key lies in searching for gamma-ray bursts, extremely energetic flashes of radiation. These bursts are often linked to violent events like supernovae or the mergers of galaxies. But some scientists theorize that a smaller population of gamma rays might be produced by the decay of antimatter particles. These particles, if they exist, would be incredibly short-lived, transforming almost instantly into matter and energy upon their creation. Detecting even a tiny fraction of these bursts could provide vital insights into the conditions present during the early universe and the processes that led to the matter-antimatter imbalance. Several research teams have been developing and deploying specialized instruments designed to capture these faint gamma rays. One particularly promising approach involves utilizing space-based telescopes like the Fermi Gamma Ray Space Telescope. The Fermi telescope is equipped with several detectors, each designed to identify specific energy ranges within the gamma ray spectrum. Researchers analyze the data, looking for any statistically significant excesses of gamma rays that don't fit neatly into known astrophysical explanations, such as supernova remnants. The challenge here isn't just identifying the gamma rays themselves, but also distinguishing them from background noise and other sources of radiation. Beyond simply looking for gamma rays, scientists are exploring the possibility of detecting photons produced by the decay of dark matter particles. Dark matter, which makes up roughly 85% of the universe's mass, is another significant mystery. While we can't directly see it, its gravitational effects are evident in the rotation curves of galaxies, like Andromeda. Some theoretical models propose that dark matter consists of weakly interacting massive particles, or WIMPs. If WIMPs exist, they would slowly decay, emitting gamma rays as they transform into ordinary matter. The energy of these gamma rays would be characteristic of the WIMP's mass and decay rate. The search extends to investigating the potential for monopoles, exotic particles that would have been produced in abundance during the Big Bang if the laws of physics were slightly different. Monopoles, possessing a magnetic charge but no electric charge, would rapidly decay, releasing bursts of high-energy photons. Identifying such bursts would provide incredibly strong evidence for physics beyond the standard model, the current framework describing all known fundamental particles and forces. The problem, of course, is that monopoles, if they exist, are incredibly difficult to detect due to their weak interactions. The work isn't limited to purely passive observation. Researchers are investigating the possibility of creating controlled antimatter annihilation events within specialized laboratory experiments designed to mimic the conditions that might have existed in the early universe. These experiments, often utilizing powerful particle accelerators, aim to generate and study high-energy collisions, hoping to produce fleeting signatures of antimatter particles. Data from these experiments can then be compared to observations of Andromeda's gamma ray emissions, allowing scientists to refine their models and search for correlations. Another avenue of research involves advanced simulations. By creating detailed computer models of Andromeda's evolution, including the formation of supernovae and galaxy mergers, scientists can predict the types and intensities of gamma ray emissions that would result. These predictions are then compared to actual observations, helping to identify any discrepancies that might point to the presence of previously unknown phenomena, such as antimatter production. The sheer complexity of these simulations, modeling billions of stars and their interactions, demands immense computational power. The search for antimatter in Andromeda is therefore a multifaceted effort, combining observational astronomy, theoretical modeling, and laboratory experimentation. It's a testament to human curiosity and our determination to unravel the deepest mysteries of the universe. The challenges are immense, and the signals are incredibly faint, but the potential reward, understanding the fundamental imbalance of matter and antimatter in the cosmos, is worth the effort. The future of this research hinges on the development of even more sensitive detectors and increasingly sophisticated simulations, pushing the boundaries of our knowledge and potentially reshaping our understanding of the universe's origins. Andromeda, our galactic neighbor, isn't just a swirling pinwheel of stars. It's a place of profound complexity, a cosmic laboratory where the very building blocks of new stars are constantly being forged. For many years, astronomers simply saw it as a grand, beautiful galaxy. But closer study revealed a remarkable and intricate secret hidden within its seemingly smooth appearance. Vast, dark dust lanes winding their way across its spiral arms. These weren't just random gaps in the light. They were dense, substantial regions of interstellar material, and they held the key to understanding the galaxy's ongoing star formation. The discovery of these dust lanes began with the rise of more powerful telescopes, particularly those equipped with infrared light. Visible light, like the light we see with our eyes, is scattered and absorbed by dust. But infrared light, with its longer wavelengths, can penetrate this haze, allowing us to peer deeper into the heart of Andromeda. Initial observations revealed a pronounced darkness within the galaxy's spiral arms, much darker than expected based solely on the visible star density. The darkness wasn't uniform. It existed in broad, sheet-like structures that seemed to trace the paths of the galaxy's spiral arms. What exactly were these dark lanes made of? The answer, as with many things in space, is a mixture. They're predominantly composed of tiny solid particles, far smaller than grains of sand, ranging in size from a few micrometers to a millimeter across. These particles aren't made of one single element. They're a complex cocktail of silicates, compounds containing silicon and oxygen, the building blocks of rocks, carbon compounds, and icy materials. Some researchers believe they also contain heavier elements, remnants from the supernovae explosions that peppered Andromeda's history. The sheer density of these dust particles means that any light passing through them is significantly scattered and absorbed. It's like shining a flashlight through a dense fog. The beam spreads out, dims considerably, and ultimately much of the light is lost. This obscuration is what created the dark lanes we observe. However, it's not simply a blank void. The dust lanes aren't empty spaces. They're the sites of intense star formation. The interaction between these dust lanes and the gas clouds within them is what triggers the process of star birth. Massive clouds of molecular hydrogen, the raw ingredient for star formation, frequently collide with these dust lanes. These collisions aren't gentle brushes. They're dramatic encounters where the kinetic energy of the gas clouds is abruptly halted. This sudden deceleration is crucial. When the gas compresses, it heats up dramatically. The pressure increases, and eventually the gas becomes so dense that gravity takes over. The cloud begins to collapse inward upon itself, driven by the immense gravitational pull of its own mass. This collapsing cloud fragments into smaller, denser clumps. Each of these clumps continues to collapse, becoming hotter and denser as it shrinks. Eventually, the core of each clump reaches a critical temperature, around 10 million degrees Celsius, where nuclear fusion ignites. This is the moment a star is born, converting hydrogen into helium and releasing tremendous amounts of energy in the process. The dust lanes themselves play a vital role in this process. They act as gravitational attractors, drawing in more gas from the surrounding interstellar medium. This influx of material continually replenishes the gas clouds, ensuring a steady supply of fuel for star formation. Furthermore, the dust within the lanes shields the nascent stars from the intense ultraviolet radiation emitted by the already formed, hotter stars, allowing them a chance to survive and grow. Interestingly, the amount of dust within Andromeda's spiral arms isn't evenly distributed. Some regions are significantly dustier than others, suggesting that the galaxy has experienced periods of intense star formation, bursts, followed by periods of relative quiescence. These bursts, driven by the collapse of large molecular clouds, led to the creation of vast numbers of new stars, and subsequently to a greater abundance of dust. Scientists study the characteristics of the dust, such as its composition and distribution, to understand the history of star formation in Andromeda. By analyzing the light emitted by stars formed within these dusty regions, they can determine the age and chemical makeup of these stars, providing valuable clues about the galaxy's past. Moreover, the dust isn't static, it's constantly being created and destroyed. Supernovae explosions, the violent deaths of massive stars, inject huge amounts of heavy elements into the interstellar medium, enriching it with the materials necessary to form new dust grains. The study of Andromeda's dust lanes offers a profound window into the life cycle of galaxies, illustrating the interconnectedness of star formation and the interstellar medium. It's a dynamic interplay of gravity, pressure, and radiation, constantly shaping and reshaping the structure of this magnificent galactic neighbor. Future observations with even more powerful telescopes will undoubtedly reveal even more intricate details about the composition and behavior of these dark lanes, deepening our understanding of one of the most captivating sights in the universe. The vastness of the Andromeda Galaxy is, in many ways, more than just its size. It's a place of incredibly subtle forces. While we've spent considerable time examining the visible effects of gravity, the distribution of dark matter, and the impact of dust, another invisible player has been steadily coming into focus: the galactic magnetic field. It's a field that wraps around Andromeda, influencing the movement of everything within it, from individual stars to vast clouds of gas, and offering a unique window into the galaxy's chaotic youth. Measuring this magnetic field wasn't a simple task. Unlike the Earth's magnetic field, which we can directly measure with compasses and satellites, Andromeda's magnetic field is incredibly weak, perhaps 1,000 times weaker than Earth's. Direct measurement requires incredibly sensitive instruments. The primary tool has been the European Space Agency's Gaia spacecraft. Gaia isn't just a star mapper. It's subtly detecting the swirling motion of stars, and this motion is intimately linked to the presence and strength of the magnetic field. As stars orbit the galactic center, the magnetic field exerts a torque, or twisting force, on them, influencing their paths in ways that go beyond just gravity. Gaia's observations reveal that Andromeda's magnetic field isn't uniform. It's not like a smooth, gentle blanket. Instead, it's characterized by significant variations in strength and orientation. The field is strongest in the galaxy's disk, particularly in the spiral arms, where star formation is most active. This heightened activity is key. The intense magnetic field isn't just a passive bystander. It actively participates in shaping the environment within these regions. The way Gaia detects this swirling motion, known as stellar sidereal motion, is crucial. Each star has a preferred orbital plane, influenced by the magnetic field. By carefully tracking the wobble, the tiny changes in a star's apparent position, scientists can deduce the direction and strength of the magnetic field at that star's location. It's akin to listening to the subtle hum of a giant instrument, each star a note contributing to the overall melody. Furthermore, the magnetic field is strongly linked to the distribution of ionized gas, the hot, electrically charged gas that makes up much of the interstellar medium in Andromeda. This ionized gas is incredibly sensitive to magnetic fields, and it's thought to be the primary carrier of the magnetic field itself. Charged particles, accelerated by stellar winds and supernova explosions, become trapped and spiraled around magnetic field lines, creating a complex, three-dimensional network. These networks are incredibly dynamic, constantly being shaped and reshaped by the ongoing activity within the galaxy. The implications of this discovery are profound. It suggests that the magnetic field played a far more active role in the early evolution of Andromeda than previously thought. Simulations now indicate that the magnetic field likely acted as a scaffold, guiding the movement of gas and dust, funneling material towards the galactic center, and ultimately fueling the intense bursts of star formation that characterize the galaxy's formative years. Without a magnetic field, the distribution of gas and dust would have been far more chaotic, and star formation would have been significantly less efficient. It's hypothesized that the magnetic field may have even influenced the very structure of the spiral arms themselves. The field could have concentrated gas and dust along the spiral arms, creating denser regions that triggered star formation. Conversely, it could have prevented the formation of dense molecular clouds, the cradles of new stars, in regions where the magnetic field was particularly strong. Another fascinating aspect of this research is the potential connection between the galactic magnetic field and the propagation of cosmic rays. Cosmic rays are high-energy particles, originating from distant sources like supernovae that bombard galaxies. The magnetic field acts as a highway, channeling these particles throughout Andromeda, guiding them across vast distances. The study of cosmic rays offers another window into the dynamics of the magnetic field and the violent processes that occur within the galaxy. The magnetic field's influence isn't limited to large-scale structures. It also affects the motion of individual stars, particularly young, rapidly rotating stars. These stars, known as rapid rotators, are strongly influenced by the magnetic field, often exhibiting highly elliptical orbits that wouldn't be predicted by gravity alone. Detecting and studying these rapid rotators provides crucial data for refining our understanding of the magnetic field's properties and its impact on stellar evolution. Current research is focused on improving the precision of Gaia's measurements and extending its observations over a longer period. This will allow scientists to track changes in the magnetic field over time, providing a valuable record of the galaxy's evolution. The ability to monitor these changes will help to disentangle the complex interplay between gravity, magnetic fields, and star formation. Moreover, scientists are developing new theoretical models to better understand how the magnetic field interacts with the plasma, the fourth state of matter that dominates the interstellar medium. These models will help to predict the future behavior of the magnetic field and its continued impact on the evolution of Andromeda. The investigation of the galactic magnetic field is a truly collaborative effort, combining cutting-edge technology with sophisticated theoretical models to unlock the secrets of one of the most magnificent galaxies in the universe. It's a testament to our ongoing quest to understand the fundamental forces that shape the cosmos, reminding us that even the most subtle forces can have a profound impact on the grand scale of galactic evolution. The universe doesn't simply collide, it dances. And the impending dance between the Milky Way and Andromeda is one of the most intricate, beautiful, and incredibly complex dances of all. We've spent considerable time observing the galaxies directly, analyzing their light, studying their dust, measuring their magnetic fields. But the sheer scale and time frame of this merger demanded a different kind of approach. Scientists began to construct a sophisticated, virtual version of the process, a massive gravitational simulation designed to predict how the two galaxies would intertwine over billions of years. These simulations aren't like playing a video game. They're painstakingly detailed recreations of reality, governed by the fundamental laws of physics. At its core, the simulation uses Newton's law of universal gravitation, that every particle of matter attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. It sounds simple, doesn't it? But when applied to galaxies containing hundreds of billions of stars, vast clouds of gas and dust, and the immense gravitational pull of dark matter, it becomes extraordinarily challenging. The simulation team, primarily operating from the Space Telescope Science Institute in Baltimore, employed supercomputers, machines capable of performing trillions of calculations per second, to model this interaction. They didn't just input the current position and velocity of each star. They tracked their movements, calculated how they'd interact with each other and with the surrounding gravitational fields. The key innovation was the incorporation of in-body dynamics. Traditional simulations often treated stars as point masses, which works reasonably well for large-scale structures. However, for a merger of this magnitude, the individual stars, distinct masses and positions mattered profoundly. In-body dynamics meant that each star was represented as a distinct object with its own mass, velocity, and position, constantly being nudged and influenced by the gravitational forces of all the other stars in the system. This level of detail allowed the simulation to capture the intricate, chaotic movements that would eventually shape the final form of the Milky Andromeda hybrid galaxy, which scientists tentatively call Milkomeda. The simulation's inputs were based on the best observational data available. The positions and velocities of stars measured through techniques like the Proper Motion Survey and the Gaia mission. The team also included estimates of the distribution of dark matter, a mysterious substance that makes up about 85% of the universe's mass, but doesn't interact with light, making it invisible to telescopes. Because dark matter's gravity dominates the motion of galaxies, accurately modeling its distribution was absolutely critical. The simulation divided the space around each galaxy into a three-dimensional grid, with each grid point representing a potential location for a dark matter particle. The simulation ran through countless snapshots over a period of 10 billion years, constantly updating the positions and velocities of all the particles. Within these snapshots, complex phenomena emerged. Stars were flung into new orbits, gas clouds were compressed and triggered star formation, and tidal forces, the stretching and distortion of matter by gravity, began to tear apart the outer regions of both galaxies. The team meticulously analyzed these outputs, searching for patterns and confirming the simulation's predictions against observations. It wasn't a perfect match at first. The simulation needed adjustments, refining the models of dark matter distribution, improving the accuracy of the star's initial velocities, and incorporating more sophisticated algorithms to handle the chaotic interactions. One of the most fascinating aspects of the simulation revealed the creation of a halo around the merged galaxy. This halo, a vast, diffuse region of stars and gas, would be a byproduct of the tidal forces tearing apart the galaxies. It's a kind of cosmic debris field, a leftover remnant of the intense gravitational interactions. Scientists believe this halo would be significantly larger and more diffuse than the halos typically observed around smaller galaxies. The simulation demonstrated that the rate of star formation within this halo would be remarkably high, leading to the birth of a huge population of new stars, a process that would dramatically alter the galaxy's color and composition. Furthermore, the simulation helped scientists understand the complex structure of the future galaxy. It showed that the Milky Way's iconic spiral arms wouldn't simply disappear. Instead, they'd become distorted and interwoven with the remnants of Andromeda's structure, creating a breathtaking, irregular shape. The simulations predicted that the merger would ultimately lead to a more chaotic, less symmetrical galaxy than either the Milky Way or Andromeda were on their own. The sheer energy released during the collision, the gravitational waves rippling through space-time, would have profound consequences, reshaping the entire galaxy over billions of years. The models demonstrated that the merger wasn't a sudden, catastrophic event, but a prolonged, complex process of accretion and interaction, a cosmic ballet of gravitational forces. The ongoing refinement of these simulations is a testament to the power of combining theoretical modeling with observational data. It's allowing scientists to not just predict the future of the Milky Way and Andromeda, but to understand the fundamental processes that govern the evolution of galaxies throughout the universe. It's a beautiful demonstration of how the most complex phenomena in the cosmos can be unraveled, one gravitational interaction at a time. The James Webb Space Telescope, a marvel of modern engineering, is constantly peering back into the distant universe, searching for clues about galaxies like Andromeda. But it doesn't just see the bright light of stars. It also detects faint, hidden signals, the subtle glow of ionized hydrogen. These observations, particularly focused on the Lyman alpha emission from Andromeda's molecular clouds, are revealing a surprising level of detail about the processes occurring within this neighboring galaxy. Lyman alpha emission is a specific wavelength of ultraviolet light produced when hydrogen atoms gain energy and then release it when they return to their normal state. It's like a tiny flash of light, incredibly weak, but remarkably abundant in the universe, especially within regions of dense gas. Scientists use Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, to detect this light. Because the Lyman alpha photons are absorbed by the dust present in Andromeda, they're redshifted, stretched out to longer wavelengths before they reach us. MIRI is particularly crucial for this research because it's sensitive to the longer wavelengths where the redshifted Lyman alpha emission resides. The initial data, however, wasn't simply a bright blob representing all the hydrogen in Andromeda. Instead, the telescope showed a mosaic of distinct emission regions, each with its own characteristic brightness and spatial distribution. These regions are identified as molecular clouds, vast, cold, and dense areas of gas, and dust where stars are born. But the Webb observations go far beyond simply detecting the presence of these clouds. The strength of the Lyman alpha emission is directly related to the density of the hydrogen gas within each cloud. Higher densities mean more hydrogen atoms are being ionized, leading to a brighter emission signal. This allowed astronomers to map the distribution of these molecular clouds in unprecedented detail. What's even more fascinating is that the shapes of these emission regions aren't always smooth and rounded like we might expect. Some appear fragmented, broken up into smaller, more irregular pieces. These irregularities suggest that the molecular clouds themselves are far from uniform. They're turbulent, jostled by gravitational forces, and interacting with each other. Webb's sensitive instruments capture variations in brightness across these regions, indicating localized fluctuations in density and velocity. Several theories attempt to explain these fragmented shapes. One possibility is that the clouds are being disrupted by the gravitational influence of nearby star clusters. These clusters, containing young, massive stars, exert strong tidal forces, pulling on the surrounding gas and creating instabilities. Another idea is that the clouds are experiencing complex shear flows, patterns of movement driven by the interactions of gas streams and magnetic fields. Magnetic fields, as previously investigated in Andromeda, play a significant role in channeling gas flow and can contribute to the fragmentation of these clouds. The observations have also unveiled a surprising connection between the distribution of molecular clouds and the presence of young, hot, massive stars. The brightest Lyman alpha emission is consistently found in regions where these young stars are actively ionizing the surrounding gas. These stars, born within the dense molecular clouds, are incredibly energetic and emit copious amounts of ultraviolet light, driving the ionization process. The relationship between the two is a feedback loop. The young stars ignite star formation within the clouds, and the subsequent radiation then fuels further ionization. Furthermore, the data provides evidence of significant turbulence within the molecular clouds. The irregular shapes and variations in emission strength suggest that the clouds are not static and quiescent structures. Instead, they're subject to ongoing, chaotic motions, with gas streams colliding and merging, creating ripples and disturbances. The intensity of these motions is correlated with the proximity to these hot, young stars. Webb's observations are allowing astronomers to quantify this turbulence, providing vital insights into the dynamics of star formation. The analysis of the Lyman alpha emission isn't just about mapping the distribution of molecular clouds. It's also about understanding the processes that govern star formation. By combining the emission data with information about the distribution of dust and the magnetic fields, scientists can build a more complete picture of how stars are born in Andromeda. The telescope's ability to detect these faint signals allows for a more detailed understanding of these processes compared to previous generations of telescopes. It's a crucial step in unraveling the mysteries of galaxy evolution. The ongoing investigation of Andromeda's Lyman alpha emission is creating a wealth of new information. Scientists are now employing sophisticated simulations, incorporating the data from Webb alongside models of magnetic fields and gravitational forces to test these different hypotheses and refine our understanding of star formation in this nearby galaxy. The level of detail now attainable offers a remarkably nuanced view into the cosmic fort where stars are created. The Andromeda Galaxy, a majestic spiral swirling with billions of stars, isn't just a beautiful sight. It's a dynamic laboratory, a place where the fundamental processes governing galaxies, including the creation and destruction of stars, are playing out with incredible intensity. While we've been mapping the magnetic fields that shape Andromeda's structure and simulating its future interactions with the Milky Way, another crucial factor is quietly orchestrating much of what we observe: stellar feedback. This isn't a gentle process. It's a furious, repeated cycle of birth and death that dictates the overall star formation rate within the galaxy. Stars aren't born in isolation. They begin their lives within vast, cold, dense clouds of gas and dust, what we call molecular clouds. These clouds are incredibly rich in hydrogen and helium, but they aren't uniform. They contain regions of vastly different densities, some incredibly compact and brimming with potential. Gravity, pulling at this material, eventually triggers the collapse of these denser regions, initiating the birth of new stars. As these stars begin to shine, they emit intense radiation, visible light, ultraviolet light, and X-rays back into their surrounding environment. This radiation doesn't just illuminate the galaxy, it's the beginning of feedback. The intense ultraviolet light, particularly, is devastating to the molecular clouds themselves. It strips electrons from the hydrogen atoms, ionizing the gas and heating it to incredibly high temperatures. This ionized gas is much less effective at collapsing under its own gravity. The energy radiated by these young, hot stars essentially pushes back against the gravitational forces trying to pull more material into the cloud. It's like a cosmic firecracker, a sudden burst of energy that disrupts the delicate balance. Furthermore, the stellar winds streams of charged particles ejected from the stars themselves add to the disruptive effect. These winds, flowing outwards at tremendous speeds, carry away the surrounding gas, preventing it from accumulating and forming new stars. They're like a relentless vacuum cleaner, sucking up the raw material needed for star birth. The size and intensity of these stellar winds depend heavily on the type of star. Massive, short-lived stars produce far more powerful winds than their smaller, longer-lived counterparts. But the process doesn't end with heating and stripping. As massive stars reach the end of their lives, they undergo a spectacular, explosive death in supernova events. These supernovae are among the most energetic events in the universe. The core of a massive star collapses under its own gravity, triggering a cataclysmic explosion that releases an enormous amount of energy and heavy elements into the surrounding space. The sheer force of these explosions can completely disrupt even the most robust molecular clouds, shattering them into smaller fragments. The heavy elements created in the cores of dying stars, elements heavier than hydrogen and helium, are dispersed throughout the galaxy by the expanding supernova remnants. This enriched material then becomes the building blocks for future generations of stars and planetary systems. It's a cosmic recycling system, a beautiful and violent demonstration of how stellar death feeds star birth. Scientists are now using detailed observations of Andromeda's stellar populations, the ages, types, and distribution of its stars, to study this feedback process in more detail. By analyzing the light emitted by stars of different ages, they can reconstruct the history of star formation in Andromeda. For example, the abundance of heavy elements in older stellar populations provides a record of the past supernova events. The presence of a large population of young, massive stars is a strong indicator of ongoing star formation, while the relative scarcity of these stars suggests that feedback is actively suppressing the birth of new ones. The interplay between star formation and feedback is a delicate balancing act. Without feedback, Andromeda would be choked with gas and dust, and star formation would proceed unchecked, eventually leading to the galaxy's collapse. Conversely, if feedback were too weak, star formation would continue indefinitely, eventually exhausting the galaxy's supply of gas. The observed star formation rate in Andromeda, a relatively stable rate compared to some other galaxies, suggests that feedback is operating at a level that maintains a healthy balance. Current research is focusing on understanding how the distribution of stellar masses influences feedback. It's hypothesized that galaxies with a higher proportion of massive, short-lived stars will experience more intense feedback, and consequently, a lower star formation rate. The observations of Andromeda's stellar populations are providing crucial insights into these complex relationships. Ultimately, studying stellar feedback in Andromeda and in other galaxies is helping us understand the fundamental processes that shape the evolution of galaxies throughout the universe, from their initial formation to their eventual demise. It's a story of destruction and creation, a cosmic dance between birth and death that continues to unfold across billions of years. The heart of Andromeda, a spiral galaxy millions of light years away, is a place of constant, subtle transformation. While the grand, dramatic events of galactic collisions and star formation cycles dominate our understanding of its evolution, another, equally fascinating process unfolds in the quiet spaces between the brightest stars. Astronomers have turned their attention to the study of planetary nebulae within Andromeda, seeking to observe the final, luminous stages of aging stars and the beautiful, transient structures they create. These aren't the gas giants of our solar system. Instead, a planetary nebula is the expelled outer atmosphere of a dying star, a shell of ionized gas sculpted by the star's intense radiation pressure. Initially, these objects were largely overlooked. Early observations focused on the intense light of star formation regions or the bright glow of massive, short-lived stars. However, with the advent of more sensitive telescopes, particularly those operating in ultraviolet and visible light, a new appreciation for their beauty and scientific value began to grow. The Hubble Space Telescope, with its unparalleled resolution and access to wavelengths blocked by Earth's atmosphere, has been particularly crucial in unveiling the intricate details of these galactic phenomena. The process begins with a star nearing the end of its life. Once a star has exhausted the hydrogen fuel in its core, it begins to fuse heavier elements, progressing through stages of helium, carbon, and eventually silicon fusion. This process generates intense heat and pressure, causing the star's outer layers to expand dramatically, transforming it into a red giant. This expansion isn't a violent expulsion. It's a slow, steady outward push. As the core continues to contract, it heats up further, and the outer layers are stripped away by the star's strong stellar winds, streams of charged particles rushing outwards at tremendous speeds. These winds collide with the surrounding interstellar medium, the gas and dust that permeates the galaxy. These collisions are what create the planetary nebula's characteristic shape. The expanding gas interacts with the magnetic fields of the interstellar medium, causing it to channel and distort the ejected material. The shape isn't random. It's often bipolar, meaning it has two distinct lobes or channels emanating from the star's central point. The exact reason for this bipolarity is still a topic of active research, but several theories exist. One prominent idea suggests that the magnetic field of the progenitor star plays a crucial role, acting like a guiding hand to sculpt the expanding shell. The gas within the planetary nebula is incredibly hot, reaching temperatures of tens of thousands of degrees Kelvin. This extreme heat causes the atoms in the gas to become ionized, meaning their electrons are stripped away, leaving them carrying a positive charge. When this ionized gas is illuminated by the central, now white dwarf star, it emits light at specific wavelengths, primarily in the ultraviolet range. This is where the observational techniques become incredibly powerful. By analyzing the light emitted at these wavelengths, astronomers can study the composition, density, and temperature of the nebula with remarkable precision. The colors we sometimes see in images of planetary nebulae are actually the result of the emission of light from different elements within the nebula. Oxygen, for example, emits a characteristic green light, while hydrogen produces red light. Nitrogen emits blue light. The interplay of these different emissions creates the stunning palette of colors that adorn these galactic masterpieces. Furthermore, the study of planetary nebulae provides valuable insights into the processes of stellar nucleosynthesis, the creation of heavier elements within stars. As the star dies, it undergoes a final catastrophic event known as a type II supernova if it's massive enough. However, even in less massive stars, the nuclear fusion processes create elements like carbon, oxygen, and neon, which are then dispersed into space during the supernova. These elements, along with those forged in the dying star itself, become the building blocks for future generations of stars and planetary systems. The material that forms planetary nebulae is therefore directly linked to this cosmic recycling process. Within Andromeda, astronomers are particularly interested in studying the diversity of planetary nebulae. Not all nebulae are symmetrical bipolar structures. Some are round, donut-shaped, or even irregular in form. This variation suggests that there's a wide range of physical conditions and evolutionary pathways among dying stars. Detailed spectroscopic analysis, the examination of the light emitted by the nebula to determine its composition, has revealed that many planetary nebulae contain heavy elements like magnesium, iron, and silicon, indicating that the progenitors of these nebulae were particularly metal-rich. The abundance of heavy elements in Andromeda's planetary nebulae provides clues about the star formation history of the galaxy, when and how metal-rich stars formed. By tracking the evolution of planetary nebulae over time, scientists can also gain a better understanding of the processes that govern stellar winds and mass loss. These processes are crucial for determining the final fate of a star and the amount of material it contributes to the interstellar medium. The study of planetary nebulae in Andromeda is a slow, meticulous process, requiring long observing campaigns and sophisticated data analysis. However, with each new discovery, we gain a deeper appreciation for the complex and beautiful processes that shape galaxies and the universe itself. They are not just transient objects of light, but living records of stellar evolution, whispering secrets about the origins of the elements and the ongoing cycle of birth, death, and rebirth that defines the cosmos. The James Webb Space Telescope, a truly magnificent machine, continued its tireless vigil, peering deeper into the heart of the Andromeda Galaxy. Its infrared vision, unlike anything we'd ever seen before, wasn't simply about seeing more stars. It was about unlocking secrets held within the very explosions of those stars themselves. Scientists had long suspected that a particular type of stellar event, a type Ia supernova, played a crucial role in the evolution of galaxies, including our own. These weren't your typical supernova explosions, the ones caused by massive stars collapsing at the end of their lives. Type Ia supernovae were linked to white dwarfs, the incredibly dense remnants of smaller stars that had accumulated material from a companion star. When a white dwarf reached a critical mass, it triggered a runaway nuclear reaction, detonating with remarkable consistency, making them excellent standard candles, objects of known brightness that could be used to measure distances across vast stretches of space. The initial detection of type Ia supernovae within Andromeda relied heavily on the telescope's ability to observe the faint infrared glow left behind after the explosion. These supernovae, even after their initial, brilliant outbursts, continue to emit significant amounts of infrared radiation for a considerable time, a far more persistent signal than their visible light counterparts would have offered. It was like searching for a faint ember glowing within a vast, dark forest. The key was finding the right wavelength of light, infrared, which could penetrate the dust and gas that often obscured the supernova's early stages. The telescope's mid-infrared instrument, MIRI, was particularly adept at this, allowing scientists to identify these faint signatures with increasing accuracy. Early observations suggested that Andromeda wasn't just a single, spectacular event. Instead, the telescope detected several type Ia supernovae occurring across different regions of the galaxy. This was a monumental discovery, transforming our understanding of Andromeda's history. Previously, it was assumed that these events were rare occurrences, punctuating the galaxy's development. Now, it became clear that they were far more common, suggesting a dynamic, ongoing process of stellar evolution and interaction within the galaxy. Crucially, the precise timing of these detections, coupled with the infrared data revealing the supernovae's spectral characteristics, specifically the ratios of different elements present in their light, allowed astronomers to establish a robust distance scale for Andromeda. Each supernova served as a benchmark, providing a known luminosity that could be compared to the observed brightness of other objects within the galaxy. By analyzing these comparisons, scientists could calculate distances with a level of precision previously unattainable. It was akin to using a ruler, a precisely measured standard, to determine the length of other objects. The distances derived from these type Ia supernovae were not just numbers. They painted a vivid picture of Andromeda's structure and evolution. Initial measurements indicated that the supernovae were located at varying distances from the galaxy's center. Some were relatively close, within a few thousand light years, while others were significantly further away, extending the reach of the observations by tens of thousands of light years. This revealed a complex, layered structure to Andromeda, with different stellar populations, younger, hotter stars closer to the center and older, cooler stars further out. Furthermore, the distribution of type Ia supernovae was not random. They seemed to be concentrated in areas of active star formation, regions where new stars were being born. This suggested a strong link between the creation of new stars and the triggering of these powerful explosions. Perhaps the accumulation of material onto white dwarfs, leading to their eventual detonation, was fueled by the dense gas and dust clouds where young stars were actively forming. It was a feedback loop, where stellar explosions influenced star formation and vice versa. As the James Webb Space Telescope continued to gather data, the precision of the distance measurements steadily improved. Scientists refined their techniques, incorporating more sophisticated models of supernova behavior and refining the analysis of the infrared spectra. The telescope's ability to simultaneously observe the supernova and its surrounding environment, the gas and dust clouds it had disturbed, provided invaluable context. This allowed scientists to study the effects of the explosion on the interstellar medium, gaining insights into how supernovae shaped the evolution of galaxies. The discovery of type Ia supernovae within Andromeda fundamentally altered our understanding of the galaxy's age and composition. The presence of these consistent, standard candle explosions provided a way to date the galaxy's formation, to estimate when the first supernovae had occurred, and how long ago Andromeda had reached its current state. It was a crucial step in unraveling the history of our galactic neighbor, revealing a dynamic and complex story written in the light of exploding stars. It was a testament to the power of observation and the ingenuity of the James Webb Space Telescope, providing a window into the past and illuminating the intricate processes that shaped the Andromeda Galaxy. The most immediate and dramatic consequence of Andromeda's relentless motion isn't a sudden, cataclysmic smash, but a slow, continuous dance of expansion. For billions of years, Andromeda has been steadily growing, pulling in smaller dwarf galaxies like the Canis Major Dwarf and the M32, effectively adding to its mass and increasing its gravitational influence. This accretion process, driven by gravitational attraction, isn't a violent tearing apart. Instead, these smaller galaxies are gently drawn into Andromeda's sphere of influence, their stars becoming incorporated into Andromeda's overall system. As these galaxies merge, their stars mix, creating a more complex, multi-population stellar environment. This mixing is crucial because it alters the very composition of Andromeda's stellar populations, leading to a richer, more diverse set of ages and metallicity. galaxies. The abundance of elements heavier than hydrogen and helium. The trajectory Andromeda is currently on, dictated by the precise interplay of gravity and dark matter, will inevitably lead to a head-on collision with the Milky Way. Current estimations, based on the most accurate measurements of Andromeda's velocity and distance, point to a collision occurring approximately 4.5 billion years from now. However, it's essential to understand that collision in this context isn't a moment of intense, disruptive impacts. Space, even across vast distances, isn't empty. It's permeated by a tenuous medium of gas and dust, the intergalactic medium, IgM. This IgM acts like a cosmic cushion, damping the forces involved. As the two galaxies approach, they won't slam directly into each other. Instead, the IgM will cause the galaxies to slow down significantly, like two cars approaching each other at low speeds on a highway. This gradual deceleration will extend the period of interaction to perhaps 1 billion years. During this time, the stars themselves will begin to interact in a far more noticeable way. Stars will be flung outwards, creating vast, swirling streams of stars. These are sometimes referred to as tidal tails. These aren't new stars forming, but rather the gravitational sculpting of existing ones as their orbits are disrupted. The galaxies will distort each other's shapes, stretching and warping their spiral arms. The gravitational forces involved are staggering. The combined mass of the Milky Way and Andromeda is equivalent to roughly 2 trillion times the mass of our Sun. This immense gravity will generate tremendous forces, enough to significantly alter the structure of both galaxies. The spiral arms, those beautiful, winding patterns of stars, will become blurred and less distinct. The dark matter halos, the invisible, immense structures of dark matter that surround both galaxies and provide the majority of their gravitational binding, will also merge, creating an even larger, more complex halo. It's a process of gradual, immense gravitational reshaping. What will become of the Milky Way after this encounter? The most widely accepted theory suggests that, after the initial merging and disruption, the Milky Way will eventually settle into a new, more elliptical shape, a structure often referred to as a milkomeda or milkdromeda. This new shape would be a giant, irregular galaxy, far larger and more complex than either the Milky Way or Andromeda are today. The original spiral arms will be long gone, replaced by a more amorphous structure. The distribution of stars will be highly uneven, with dense clusters interspersed with vast, empty voids. The fate of our solar system is a subject of intense speculation. While it's highly improbable that our sun will be directly consumed, galaxies don't typically swallow up entire stars. The gravitational environment around our location within the Milky Way will undoubtedly be radically transformed. The orbits of the stars around the sun will be perturbed, potentially leading to unpredictable shifts in our solar system's position over time. The long-term stability of the solar system is, therefore, uncertain, though current models suggest that it would remain relatively intact for a very long period. The collision and subsequent merger of the Milky Way and Andromeda represents one of the most spectacular events in the history of the universe. It's a fundamental process driving the evolution of galaxies, creating the complex and diverse structures we observe today. This grand event, playing out over billions of years, ultimately contributes to the ongoing expansion of the universe. Even after the initial merger, the Andromeda Galaxy will continue to interact with its surroundings, gravitationally capturing smaller galaxies and contributing to the overall growth of the local group, a cluster of galaxies bound together by gravity. The future isn't about destruction, but about transformation, a slow, grand dance of galaxies forging a new, larger universe. This process continues on a cosmic scale, shaping the very fabric of space and time. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Now, let your thoughts drift gently with the light of Andromeda, distant and serene. Allow your mind to settle, unhurried and calm until sleep finds you.